All right, welcome to the next screencast for Honors Chem. This is going to be objective 11, 12, and 13. We're going to start off with objective number 11. We're going to analyze various forms of energy. There are all different types of energy that can be found. Energy is not matter because remember it does not take up space and it does not have mass. But energy is the ability to do work. So it's the ability for matter to do what it needs to do and move. We think of movement as kind of the primary way to show something has energy. There's magnetic energy, kinetic energy, heat energy, also known as thermal, light energy, also known as radiant, potential energy, chemical energy, that's what we find in chemical bonds. That's the energy that's broken or released during a chemical reaction. Sound energy, electrical energy, and nuclear energy. These are kind of the main forms that we see energy in. Potential just means that it's stored, so it's not being used yet, and kinetic means that it's being used, so that's energy at work. And here's a diagram just showing some different potential versus kinetic energies. Heat transfer is whenever you get energy transferred from one body to another due to a temperature difference. So wind is a heat transfer, going from high energy to low energy. That's where you get wind flowing from. But temperature is the measure of how much thermal energy a body has. So we use temperature to measure heat. We do not measure cold, but the heat. So coldness is simply the lack of heat. So something feels cold because it doesn't have any heat energy or it doesn't have as much heat energy as the surroundings. Okay, objective number 12, compare and contrast between endothermic and exothermic reactions. This is what our labs are going to be on today. By knowing a little bit about prefixes, you can figure out what endothermic and exothermic mean. Endo means in and therm means heat, so these are going to be reactions that take in heat. Ex means out and therm means heat again, so these are reactions that are going to give off heat energy. So chemical reactions that change in thermal energy, so if you see a change in thermal energy, they can be endothermic or they can be exothermic. In an endothermic reaction, heat is absorbed. Thermal energy is going to be listed as a reactant. So in the actual chemical reaction, you will see energy listed as a reactant instead of a product. In exothermic reaction, heat is going to be released, and you will see thermal energy listed on the product side. So if something is measured in kilojoules and it's given to you on the product side, you know that it's an exothermic reaction. A little bit about enthalpy. Enthalpy is the energy change within the reaction. So the heat energy change in H, the triangle means change in, the H means heat. That takes place when reactions go to products. So think about the whole system. If you think about the entire reaction system as you go from reactants to products, is the whole system gaining energy or is it losing energy? If heat is absorbed, so if heat is taken in, to the reaction, it's an endothermic reaction. The change in H is positive and heat is going to be listed as a reactant. So you have to think about the whole system. Heat energy is being taken in, so you are, for that system, that reaction, you are increasing in energy. If heat is released in exothermic reaction, then the change of H is going to be negative. You are losing heat to the surroundings, so you're losing energy to the surroundings. It's going to feel hot, but it's a negative change in energy availability for that reaction because it's losing it to the area around. And heat will be listed as a product. So this is what we're talking about. In an exothermic reaction, energy is released or given off. So your reactants start out here at some energy level. Then you have the reaction starting, which takes a little bit of activation energy because all reactions, that's the energy added to start a chemical reaction. All reactions take a little bit of activation energy. But you notice that as the reaction proceeds, I actually lose energy. So this is going to be a negative change in H because I'm actually losing energy. And that heat is going to be given off to the surroundings. So that heat is no longer available for the reaction. So my products end at a lower energy than my reactants. That's an exothermic reaction. In endothermic reaction, energy is absorbed or taken in by the reaction. You get a positive change in H because my reactants start out at some energy level. I have this massive amount of activation energy. Once the reaction starts, my products end at this higher level. So I've absorbed this much heat into the reaction, and I would be able to measure that as a temperature change. I have taken in this much heat energy. Even though this reaction is going to feel cold, it has a positive change in H. You're taking in the heat from the surroundings. So that's an endothermic reaction. You might go ahead and draw those two graphs in your notes as you are going to have to rely on those graphs during your lab. All right, objective number 13, examine the effects that catalysts have on chemical reactions in terms of energy. So a catalyst is pretty important in terms of the activation energy. Remember, all reactions require energy to start the breaking of the bonds. So all reactions require a little bit of activation energy. And here's showing you this particular reaction requires this much activation energy. If I add a catalyst or an enzyme to that reaction, I'm going to lower the activation energy that's needed. So different reactions have different activation energies. Reaction A, this one takes this much. Reaction B, this one takes that much. So each reaction has its own level of activation energy needed. So some reactions don't take very much activation energy, like this particular reaction doesn't take very much. Some reactions, such as iron rusting, have a low activation energy. The energy in the surroundings is enough to start these reactions, so that's why they'll happen outside at just kind of your average temperature. Other reactions have high activation energy. For example, wood requires the thermal energy of a flame to start burning. Once the reaction starts, it releases enough energy to keep the reaction going. Things aren't going to spontaneously combust or burn. Like wood's not going to burn on its own. You have to give it a trigger. So this reaction would require a lot more of activation energy to get it going. But then once it starts, it does produce enough energy to keep that reaction going. So reaction rates, that is the rate that a reaction, or the rate of reaction is the speed the reaction occurs. So how long does it take, or how fast does that reaction happen? Molecules collide before they react. So chemical reactions occur faster if particles collide more often. That's just kind of common sense. So if your particles are moving faster, or you get more collisions between them just because there's more particles, your reaction is going to happen faster. That's basic collision theory. What a catalyst does, it's a substance that increases the reaction rate by lowering the activation energy. So the normal reaction is shown to you here in red. So you would require this much activation energy, and then it would go to products. So that's without a catalyst. With a catalyst, you don't need as much activation energy, so that reaction can happen faster, and you go to products at a faster rate. So you can change the speed of the reaction by adding a catalyst. One way catalyst speed reactions is by causing reactant particles to contact each other more often. So you get more collisions, which makes the reaction occur faster. A catalyst only makes a reaction happen faster. And biological catalysts, those are your enzymes. Enzymes within your body make reactions. These special proteins make reactions happen faster. So like digestive reactions that would normally take years upon years happen in a few hours because of biological catalysts. So the reaction doesn't change the catalyst, and the catalyst doesn't change the reactants or products. A catalyst doesn't increase the amount of a reactant or a product made, and like these two that we just talked about, they only make the reaction happen faster. So they're not being used up in the reaction. They're not changing anything. They're just kind of like a side piece that you can add to this to make it go faster. We are going to do an example of one where I'm going to show you that a catalyst is not changed at all. So you can reuse the catalyst over and over and over again. So that concludes our objectives for this screencast.